a copper sulfate solution and a sodium hydroxide solution, and I mix them together, I would get what's called a precipitate. A precipitate is when you form solids from aqueous solutions. Now, these solids can literally look like solid chunks. They could be cloudy, murky. All right, so those are all signs of precipitate. What that just means is that the grain size of the solid is larger or smaller. If it's finer, then it looks cloudy, right? If it's chunks, then they're huge grain sizes, and they just sink to the bottom. So the characteristics are not the point. The point is whether something does precipitate or not. Okay. All right, so let's write a balanced equation for this reaction here. So I had copper sulfate, which is CuSO4, and it started as a solution, so the state would be aqueous. This is sodium hydroxide, which is a solution, so that state is also aqueous. Okay, and you might remember that when you have two ionic compounds reacting together, what usually happens is what's called a double replacement reaction. So in the double replacement reaction, the positive ion from the first compound bonds to the negative ion of the second compound, and vice versa. So what would be my products? Or one of them? Sure. Copper hydroxide. Now be careful, because you should, when you're writing formulas, you need to know what the charges are. The hydroxide is a -1, the copper is a +2. All right, and so that leaves then sodium with sulfate, and sodium's a +1, and sulfate is a -2, so you're going to need 2 sodiums on the sulfate. Okay, states, we're not discussing solubility rules in this unit, so I'm just going to write these for you. This is aqueous, but this is our solid. The funny thing about writing the state for precipitate, S means solid, but initially it could be misconstrued for soluble, but that's not what it means. S means solids. AQ means soluble. Okay. All right. There. Oh, I need to balance this. Now it's balanced. Okay. Calculate the initial quantity into moles. Into moles. I didn't give values here, but I'm gonna put values in here right now. So let's say that I had 10 milliliters of each. Okay, and let's say that the standard concentration of lab solutions is 0.1 molar. So let's say that they're both 0.1 molar to begin with. So if I want to calculate the initial quantities of copper sulfate and sodium hydroxide, I need to know how to do that. I was given a molarity, I was given a volume. How do you find the moles? If you know the volume and the molarity. Well, what did we just do? I need to multiply my molarity by my volume. I need to be in liters, though. Okay, so for the... Didn't really give myself a lot of space here. All right. For the CuSO4, we said there was 0.1 molar. And we said the volume was 10 milliliters, which in liters is 0.010 liters. So 0.1 of 0.01 is 0.001. You guys with me? Okay. And remember how the proportions were the same for the other reactant? It was 10 milliliters also. It was also 0.1 molar. So it's safe to say that we have 0.001 molar or moles of NaOH as well. Okay. We've got moles of both reactants. Determine the limiting reactant. Okay, this now becomes a limiting reactant problem. So we have a balanced equation, and what you solve for whenever there is a precipitate is the precipitate. So we're going to solve for copper hydroxide. So 0.00100 moles of CuSO4, and we're going to solve for CuOH. So 1 CuOH2 for every 1 CuSO4. So 0.00100 moles of CuOH2. That is from the perspective of copper sulfate, but remember, you always do this for however many reactants there are. So we do this again for the sodium hydroxide. And this is important because look what happens here. The mole ratio from copper hydroxide to sodium hydroxide is 1 to 2. So that means 0.0005 moles of CuOH2 are expected here. Between these two yields of my product, this is the lower amount, this is the theoretical yield, this number is irrelevant. Okay, so therefore the limiting reactant is sodium hydroxide. What is the total volume in this problem? Yeah, 20 milliliters or 0.02, right? So because we had 10 plus 10, so 20 milliliters, 0.02 liters. Okay. All right. So remember, what's the definition of limiting reactant? Runs out first, right? And we identified the reactant that ran out first as sodium hydroxide. Okay. So that means what's in solution in this beaker, right, or in this test tube right here, the solid here was our CuOH2, right? But in this test tube, there are still the ions present. The other reactant, or the other product, was sodium sulfate, right? So that means there's sodium sulfate aqueous. So let's just say sodium ions, SO4 2 minus ions, both present and floating around. They were not part of the product, so they're still there. If the limiting reactant was the sodium hydroxide, that means there's this, if we look at our balanced equation, the limiting reactant was the sodium hydroxide. What ion is present or is common between the sodium hydroxide and the precipitate? What do they have in common? Which elements do they have in common? The hydroxide, right? OH minus here, OH minus here. So what that tells us then is that the hydroxide is truly the limiting reactant. So of the sodium hydroxide, it was the hydroxide that really ran out first. So the hydroxide is gone. It's all gone. But there's still some sodium left. Okay, so when you get to this point in a problem, you need to assess the ion common to the precipitate and the limiting reactant is completely consumed, and thus its molarity is 0. In this case, hydroxide. The other ion is found in excess, which here is going to be the sodium ion. So the purpose, I'm going to add another page here just so we have more room to work. So I'm going to finish this problem here where I have more space. What we're going to do is we're going to solve for the amount used. Okay, so solving for the excess reactant. Start with the theoretical yield in moles. Okay, so what was our theoretical yield in moles? 0.0005. Okay, so since I know the theoretical yield, that's how much is going to be made. That is the maximum amount of product that can be made. I'm going to backtrace this and figure out how much of the sodium hydroxide could be made by using the mole ratios. Or, I'm sorry, was used. How much was used? So okay, so one step. Let me label this so you know what I'm doing here. This was the theoretical yield. We're solving for the excess reactant. That's why the sodium hydroxide is on top. So now I know how much sodium hydroxide was used. You know what? I just realized something. All right, let's back it up. Sorry. I don't want to solve for the sodium hydroxide. I want to solve for the other one because I know how much sodium hydroxide was used. Sorry. Let's go back and erase. Let's just change the numerator here. Okay. It's the copper sulfate. Wait a minute. Hold on. I'm getting lost in my numbers. Copper hydroxide. .05 moles. Okay, yeah, it's the copper. 1 CuSO4. So 0.0005 moles CuSO4 that were used. Okay. Yeah. I know why I got that wrong, because up here in step 5, I wrote down sodium was the excess. That's not true. It's the copper. Okay. If that's how much copper sulfate was used, do you guys remember how many moles of copper sulfate we said we began this problem with? Yes. So 0.001 mole of CuSO4 at the start minus 0.0005 moles that were used means there's 0.0005 moles of CuSO4 in excess. So the goal here is to figure out the concentrations of all 4 ions. These are our 4 ions. There's Cu2 plus, there's OH minus, there's SO4 2 minus, and there's Na plus. Now remember, we already established what the real limiting reactant was, and that reactant has a concentration of 0. Which one was it? It's the hydroxide, so 0 molar. Copper is the excess, so now that we know how many moles of copper sulfate are in excess, we need to figure out what the molarity is. Okay, so 0.0005 moles of CuSO4 in that In every CuSO4, there's one copper. I know that's kind of obvious because you look at it and you say, oh, yeah, it does, it's 1 to 1. But that's not always going to be the case. You might have coppers with like AlCl3, right? So the step needs to be shown to recognize that you are verifying the amount of copper ion that is indeed left over, which is 0.005. And we're asking for molarities, and there was a reason why they asked for you to take note of the final volume, which we said was 0.02 liters, right? So the molarity of copper is going to be this divided by 0.02 liters. .025 molar. Okay, that was the hard part. Going through all that was the hard part. Figuring out the excess reactants concentration. Now, there's 2 more ions, sodium and sulfate, but those, because they did not react, and they didn't form the product, the solid, these are what are known as spectator ions. They did not participate. So, to find their concentration is a lot more straightforward. All you do is you take the moles of what the compound was at the beginning. So let's go back and find the moles of the copper sulfate, which was 0.001. And I'm going to solve for the sulfate. There's 1 sulfate in copper sulfate, which means there's 0.001 moles of sulfate present. And because the sulfate did not react, the number of moles of sulfate is unchanged. So all I need to do is take that number of moles and divide it by what the volume is. Which will be, 0.05? And I do the same for sodium. So we had 0.001 moles of sodium hydroxide. There's, in every sodium hydroxide, there's 1 sodium ion. So 0.001 moles of sodium divided by the volume. The molarity is going to be 0.05 as well. All right, that was a big problem really fast. Let's do another sample and walk through the steps cleanly, and this time we'll have ratios that are not just 1 to 1, just so there's some kind of, way to notice what we're doing. Okay. In your typical problem, it will look like this. They'll give you the volumes, they'll give you the molarities. They'll tell you 2 things react, they'll tell you what a precipitate is, follow the same steps. So we're going to start by writing a balanced equation. All right, lead-2 nitrate. So the formula for lead-2 nitrate looks like this: PbNO3 aluminum sulfate. So aluminum's +3, a sulfate is -2, so it's going to be Al2 parentheses SO4 3. They're going to react. We're going to get lead sulfate. And they don't tell you what the other product is, but you should be able to figure that out. What's the other product? Yeah, aluminum nitrate. So Al, nitrate is -1, aluminum is +3, so we're going to need 3 nitrates on that. Okay, that's aqueous. We balance this. I always start balancing by taking the more complicated formula. So that would be the aluminum sulfate here. All right, I'm looking at this and I say, all right, there's 3 of the polyatomic ion sulfate on here. So let's do a 3 here. And then that means there's 3 leads now. So now we go to the left side and put a 3 there. And now that means there's 6 nitrates. So I go to the right side and putting a 2 here gives me 6 nitrates. And now I have 2 aluminums and now I'm done. Okay, balanced equation, done. What do I do next, guys? What are all those numbers for? Yeah, I gotta find the moles. Okay, so 0.015 liters times 0.11 moles per liter. This is how I find the first solution, which is lead nitrate. So 0.015 times 0.11, 0.00165 moles of PbNO32. Okay. The other 0.012 liters times 0.2 molar .0024 moles of aluminum sulfate. Okay, we got our moles done for both. Remember the goal. The goal is to find the concentrations of all 4 ions. So, we already know what the precipitate is. This is a limiting reactant problem. So now we use our mole ratios. And we're solving for lead sulfate. And don't forget to place the coefficient of lead nitrate down at the bottom. Okay, so that's for the first one. For the second one, you're still solving for lead sulfate, but this time you're canceling moles of aluminum sulfate. Here are our 2 possible yields. Of course, you know only one of them can be right. The theoretical yield is 0.00165. That means the limiting reactant was lead nitrate, but specifically which ion in lead nitrate is the actual limiting ion? The lead. That's the ion that's common to the limiting reactant and the theoretical yield. It's the lead, which means it was the lead that was responsible for stopping the reaction. The lead ran out first, which means the concentration of lead is what? 0. Oh, by the way, whenever you see me write brackets like this, that means concentration. Okay. All right. We have 1 of the 4. So the next one would be the ion that is in the product, but was not literally the limiting reactant. So the sulfate ion. So I want to solve for the sulfate ion. Okay. So this is our excess ion. So, what do you start with? How do I start this line of work to find the excess reactant? The theoretical yield. So, we have 0.00165 moles of PbSO4 that will be made. I need to solve for the compound that contains the sulfate. So 1 Al2SO4 3 over 3 PbSO4. Okay, so that means 0.00055 moles of Al2SO4 3 were actually used. Now, we do know how many moles of aluminum sulfate this problem began with because we had already calculated that right here. So let's take the difference. Point 0.00185 moles of excess aluminum sulfate. Now, I don't care right now about the aluminum. I just care about the sulfate, and there are 3 sulfates per formula. Which means there's 0.00555 moles of sulfate floating around. Okay, final step. Molarity of excess sulfate is the moles divided by, what's our total volume? What do we add here? We had 15 and 12, so 27. So we're going to divide this by 0.027. And that's going to be 0.21 molar. 0.205. 5555, I'm just rounding it. Okay, we have 2 of the 4 ions. And I ran out of room. I'm gonna do the rest up here, I guess. Okay, I have 2 spectator ions, guys. What are they? Aluminum and nitrate. Okay, so didn't plan this very well. Okay, so the number of moles of the aluminum started as 0.0024 moles of aluminum sulfate. In every aluminum sulfate, there are 2 aluminum ions. So that means there's 0.0048 moles of aluminum ion floating around. Aluminum is a spectator. It did not react. Therefore, we don't subtract anything from its moles. We just take the number of moles and we divide by the volume. 0.027 liters. Uh, 0.17 repeating. We'll just call it 0.18. Okay, last one. Nitrate. We had 0.00165 moles of the lead nitrate. There are 2 nitrates per formula. So that's 0.0033. The volume is 0.027. 0.12 molar nitrate. Sheesh. What a terrible problem. Who wants to do one of these again? Oh, you guys. Okay.